Hi, everyone. It's a real pleasure to be here. I'm very honored to be part of this workshop. I've been excited about it ever since I heard about this whole trimester and everything, and I'm really glad to have been able to make it at least for a few days. And among other things, I mean, the whole theme of illustration and how it interplays with math is something that's very dear to my heart. It's something that I continue to explore every day, and I'm not exactly sure what my relationship is with illustration or with drawing or with visualization. All of these things are very intriguing to me. And also, I come from a family that's more of artists than mathematicians. And so I've always been sort of the black sheep of the family. And this is, anyways, this theme in particular is very dear to my heart for that reason. And in particular, I've been thinking about this talk for over a year, I think, and I still don't know what I'm going to talk about. So this is the rough theme that's sort of underlying in this talk is the notion of moduli space. And what is a moduli space? I mean, you can define it many different ways, but from the point of view of a geometer, for me, it's a question of measuring proximity between geometric objects. And that, of course, just the question of how would you measure the distance between two triangles is a question where you could spend centuries working on it, and people have done exactly that. So I'm not the only one. But it's also something where if you're in the world of art, then the idea of proximity of how shapes relate to one another is something that you'll maybe touch at with a more intuitive feel, with a more emotional aspect. But that emotion also exists in the world of math. And so this interplay is something that's very dear to my heart. So I've sort of split the talk into three parts. Right, OK. And so I'm going to appeal to you to be active in this talk for those who are willing and have the energy to swipe left and right. Please, and this works really well if I give a talk in a high school, please get your phones out or your screens on and start playing. And you can ignore everything I say from this point, and I'll look at you being on your phones, and I'll be very impressed by how dedicated you are to my talk. So please do that. And so what this is what you're going to be looking at is, is a game called Quadratus, and the way it works is the following way. So this is just the demo on the website. So you press play, and you have a puzzle. The puzzle shuffles, and your goal is always to bring the puzzle back to its original shape. So you can move the squares around, and notice that when you move the squares around, maybe they do not exactly what you thought they might do, or maybe they do exactly what you thought they might do. But depending on. Anyways, and so I could try to solve this puzzle. Of course, it would take me hours and hours, but maybe that's just, there we go. I've decided what my talk is going to be. I'm just going to try to solve the puzzle. Okay. All right, so that's the idea of this. Oops, I did something I shouldn't have done. And I've lost my, here we go, talk entirely. Okay, so this puzzle here, you can sort of see that the underlying object behind this is a topological surface, and in fact, it's a square-tiled surface. So you create these surfaces by having squares, and each square has a top side, a bottom side, a left side, and a right side. And the rule is that you have to associate top sides to bottom sides and left sides to right sides. All right? So for instance, if this is the surface that you're on and I was an ant, then, I have to say, some of these slides I made for when I present these things to 8-year-olds. But don't worry, I'll speak really slowly. But anyways, and you're an ant, and you lie on one of these surfaces, and then you arrive here, and then because you've associated it, that's funny. This computer is very slow, hence the ant is very slow. Okay. Anyways, and so the ant goes there. Wow. Normally the ant's a lot faster. Here we go. And so the ant goes there, and then, of course, the ant has to follow where the arrows tell it to go. Uh-oh. Lights are flashing. I don't know if that's on purpose. There we go. OK. And so then, but maybe you have a more complicated shape like this one. And if you have a more complicated shape, then you have to decide how you do the side pairing. And so maybe, have a look. Everybody look at that. And so that tells you how the tops are associated to the bottoms. That's how the lefts are associated to the rights. OK, did everybody have a good look? Tops associated to the bottoms, left associated to rights. OK, we're good with this. And now if you're an ant, then of course you go across and you have to follow this. Right? OK, good. So I'm glad you all, there we go. I took the arrows off because that would have been too easy. And then, all right, does everybody know where the ant's going to go next? OK. All right, so you get the idea. And despite this very, very slow computer, the ant will eventually stop moving, I promise. OK, and then you take one of these square-tiled boards, you color it, and then this gives you a puzzle. OK, and the puzzle works in the way that the squares, when you slide them, they have to follow the same trajectory that the ant follows. So if you slide a colored square, it has to go from left to right. So but what are these boards that we're looking at? These boards are called square-tiled surfaces. And they're square-tiled translation surfaces because you're associating tops to bottoms via translations. And these translation surfaces play an important part in math. I see some people in the audience who work on these exact surfaces. And so they at least must agree with me that these are kind of important objects. And you sort of see the topology of the surface on the left. You can sort of see that it's a torus by associating left to right and top to bottom. What's maybe less obvious is that the surface on the right is actually a genus 2 surface. Of course, we're talking with an audience who signed up for a conference in geometry and topology, so I assume. But if I want to know whether this is a genus 2 surface, my instinct is actually to compute something and to see what the Euler characteristic is, rather than to try to do a mental image. Here are images from Carlos Mateos' lecture notes where you sort of see why it's a genus 2 surface visually, kind of. But it's sort of non-obvious. But luckily, you don't have to know any of this to play the game. So that's an important part. And so you take one of these boards, you color it, and then you start playing. Okay? And of course, there's many, many different ways to color the board. In this particular case, with that choice of colors, there's 630. But in general, of course, if you have a larger board, more colors, you have many, many different ways of coloring it. And there's lots of questions you can start to ask. So here's one, for instance. This is the sort of the standard torus we started off with. But if instead of doing the pasting in the top to bottom way that I've been doing up until now, if I switch it over a little bit and I do a slight twist, I still get a torus. Okay, so this time I'm pasting the top, but to 1 over on the bottom, as opposed to pasting it like that. So if I took a torus and I did a slight twist, okay, so it's still a torus. But here's sort of a question. Can you find a way of sliding these squares around to get from the figure on the left to the figure on the right? Right? So this is, it's a question, right? And it has an answer. And so one way of answering this, maybe it's not completely obvious, but one way of answering this is just focusing on the pink squares. And if you focus on the pink squares, then you notice that whenever you make a move, so you can make either horizontal or vertical moves. So if you make a horizontal move, I never know which one's horizontal and which one's vertical, so I have to think of horizon. Anyway. All right, so you make a horizontal move, and you notice that on the top row, leaving from the left, there's always going to be one pink square. Right? It doesn't change the number of pink squares on the top row. Right? So if I make a horizontal move, one pink square. If I make a vertical move, then these squares go around. I still only have one pink square on the top line. Right? So any horizontal move or any vertical move, no matter what you do, you will always have one pink square on the top line. And what I'm trying to do is I'm trying to get 3 pink squares on the top line. So it's impossible. I can never increase the number of pink squares on the top line. So it's impossible to find a movement or a sequence of movements that gets from this configuration to another configuration, right? So that's an example where we can sort of see it. But more generally, for each one of these puzzles, you have a different space that's associated to it. And in this case here, what I want you to do, so this is another website. I'm appealing to you again. So this is another website. Maybe I don't know if you can capture that QR code. But what you see here is the graph of all possible, let me get that out of the way, moves that you can get from that initial configuration on the top. So every time somebody logs on, it reconfigures sort of the graph. And you see the different colors. So when you play around with these, try to figure out where you are. Of course, it doesn't help that it keeps resetting. It's very small. All right. Whoops. So let me go back to this. If you want to try it, that's the web page. So it's Quadratus Play. You can also just type it on your computer. Okay. So while you do this, I mean, the thing I want to point out a couple of things about this. The first thing is that what you see here is the configuration space of all possible patterns that you can reach from the starting pattern. If you compute the number of patterns that you could make with that number of colors, you'll see that it doesn't correspond to the number of patterns that's here. So this is an example. This web page, this graph that you see here has 84 different nodes. And you sort of expect there to be 420. Because that's the number of different ways I can color that initial shape with those colors. And as you see, this is cool. So we're getting quite close to actually filling up the entire graph. But for instance, I don't know why this thing doesn't have 420 nodes. I know why, because I programmed it and we figured out that it didn't have 420 nodes, it had 84, but I have no idea why. And 84 happens to be 420 divided by 5. And 5 seems like a really mysterious number in this case. But anyway, so that's just an example of something we sort of don't know. Here, let me go back to this. Tell you about some things that we do know. So here's another example of one of these graphs. So in this particular graph, any two configurations are related by a move. This is sort of what they look like if you look at the whole thing. This is another example. This is the one I showed you at the very beginning, the puzzle. Here, any two configurations are related by a move. But in general, there's a lot of things we don't know. So here's something we do know. So if you start off with the original torus shape that I started off with, you get sort of a family of puzzles by increasing the size of the torus shape. And you can do that as much as you want. And you can look at distances between different patterns. And so the distance between different patterns is the number of moves it takes to go from one pattern to another pattern, right? So it's the same thing as the distance in the graph that we just saw. So it's the graph distance between any two patterns. But of course, you have to look at the minimal number of moves. And then you have a diameter of the whole puzzle space, which is the maximum number, which is the maximum size, the maximum distance of any two nodes in this graph, right? So that gives you a diameter for this space. And so you get a very natural space or a natural family of puzzle spaces just by increasing the size of the square. And this square here, well, something we showed together with Paul Turner is that the diameter of this square, or the diameter of this puzzle space, grows roughly quadratically in n. Right? It has roughly quadratic growth. So it's sort of very similar to questions you might ask about moduli spaces of surfaces or other related objects. But in general, Yeah.
You said the graph is not connected?
So in this particular case, the graph is connected. But in general, when I talk about so I mean, in general, you always start off with an initial space, an initial pattern, and then you move from that pattern. And when you move from that pattern, by definition, the graph that you get is connected because you're looking at a connected component. But in general, I'd like to point out that what's maybe more impressive about this is the things we don't know. Okay, so it's not so much the very particular puzzles where we know how to measure the diameter of these graphs, but in general, I'm much more impressed by the things we don't know. So for instance, there's no known sorting algorithm. So we don't know of an algorithm that actually solves these puzzles. Right? And even less, if we did, I mean, we don't know anything about the possible computational complexity that such an algorithm would have. I mean, of course, not knowing an algorithm is an indication that one might not know the complexity of that algorithm that you don't know. But the point is that. And in general, like even questions of how to decide whether two configurations are related by a set of moves, essentially everything we know is just sort of in particular cases we can figure out something that tells us something, but otherwise in general we don't know. And I think that these questions that are sort of behind this are really related to deeper questions about moduli spaces. So about these sort of, something that I've been sort of hinting at from the beginning is that behind these puzzles are these notions of moduli spaces. In this case, you're really looking at a moduli space of square-tiled translation surfaces. But in the background, these are very much related to moduli spaces of hyperbolic surfaces. And very intriguing objects, and there's still really a lot to be discovered. Okay. This is an example. We had people play on these at a museum at the EPFL called EPFL Pavilions about a year ago. People were allowed to play these and light up these different moduli spaces. And this is sort of the result that we got out of that. Okay, so second part of the talk, something completely different and much closer to actual hyperbolic surfaces. And that's this question. So now we're entering the realm of hyperbolic surfaces. And so sort of, as I was saying, that behind quadratus puzzles, there are hyperbolic surfaces, but where are they? Maybe it's not so obvious where they are. So we had this quadratus puzzle, and of course it had side pairings, and so it's easy to remember or to forget that the lines were there. And then from there, you can kind of see that there we go. There are the hyperbolic surfaces. And now all of a sudden, we're very happy because we see a hyperbolic surface. And of course, we keep the same side pairings as we had before. And now all of a sudden, we have a genuine hyperbolic surface. And these images here are images in the disk model of the hyperbolic plane. And this time, we have side pairings. And the objects that we get are smooth everywhere, unlike the objects that we had before, where we had singularities. Okay. And so this part here, I want to talk about pictures drawing on surfaces, sort of a project we've been doing over the past decade or so with Peter Boozer. And in this particular case, what you see here is a regular octagon where the side pairings are kind of opposite. And the object that's of interest to me here is the space of simple closed geodesics. So when you're on one of these surfaces like this, if you move geodesically across the surface, because we're in hyperbolic geometry, all the lines that you see correspond to simple closed geodesics. So they're geodesic, you go along and you come back, and simple just means that you don't have any self-intersection points. So that's the object that we're interested in. And so you can draw lots and lots of simple closed geodesics. So we're still on that original surface. This surface plays an important part. It's a genus 2 surface. It plays sort of an important role in the world of genus 2 hyperbolic surfaces. It's called the Bolza curve. Has this, and these are the sort of what the set of simple closed geodesics look like. That's one. Of course, you can deform the surface a little bit. And then you get other pictures, and then of course this also has, you deform the surface, this also has simple closed geodesics on it. And these are sort of the images that we came up with. And why we were interested in this set, well, I mean, there's a number of reasons why one cares about simple closed curves on surfaces, but in particular, a theorem of Berman and series that is quite amazing that tells us that the set of simple closed geodesics on a hyperbolic surface is nowhere dense. Right? So that means that, in fact, it has Hausdorff dimension 1, but it means that wherever you are on a surface, you can find a little region around wherever you are, where no simple closed geodesics pass. So this is very different from the case of, for instance, flat tori, where simple closed geodesics go everywhere. Right? So this is really a phenomenon of negative curvature. And it's also a phenomenon. So this is all right. So this is the. All right. So I'm very intrigued as to how this looks because I didn't know how it would look on this screen. All right. But okay. But you see, it looks the way it looks. But this is the sort of the set of, and you can tell that the Berman series theorem is true, right? Because that's clearly nowhere dense. And this is very much in contrast with the space of all closed geodesics on a surface. So if you look at all closed geodesics on a hyperbolic surface, then these ones are everywhere dense. In fact, dense in every direction of the unit tangent bundle. Okay, so this is, I mean, I guess one would attribute this to Hedlund from the 1930s. It's much, much easier to draw a picture for you of the space of all closed geodesics. Anyway, so that was much easier. So the point is that these simple closed geodesics have this very, very particular role in the space of all closed geodesics. And this is something this is an example of a theorem we just proved with Peter Buser, which was exactly trying to investigate the images that we were creating. Okay? And the origin of this theorem, and I'll tell you why in just a second, what it is at one point we sort of said, but I mean, we think that we're drawing the space of simple closed geodesics on a surface, but we weren't exactly sure that we were. Because that's not the way sort of the algorithm worked. The way the algorithm worked was that we start drawing, and after a while, we still haven't, so we sort of exponentiate in two directions, and after a while we check and make sure that the drawing that we have is still embedded on the surface, so that's something you can check. But then we stopped, right? And we didn't necessarily close up the simple closed geodesic. So we sort of went out, checked and make sure the thing was simple for a long time, and then we stopped. And this theorem here tells us that that was the right thing to do, or a right thing to do. So what this says is that never mind the functions that are there, but if you give yourself an epsilon, it says that if you go out far enough on a surface and you exponentiate in both directions, and what you get is still a simple geodesic arc, then in fact you're very close to what's called a lamination, which is a generalization of the space of simple closed geodesics. All right, so this result sort of has two corollaries. And the first corollary is that, I mean, I have to say that I should say that the pictures are correct. That really referred to the picture on my computer. They made me change computers for this talk. I don't want to blame the organizers, but no. All right. So the figures of the set of simple closed geodesics I should have added on my computer are correct. Okay, so this is sort of what they look like, and that was the first corollary. And the second corollary, and this is a more mathematical corollary, is that the space of all the space of all simple closed or simple complete geodesics can actually be made really dense. Okay, and this comes from the picture that we saw. So when we started looking at the first images that we created of the space of all these simple geodesics, we sort of said, wow, okay, so we know the Berman series theorem is true, but these look pretty dense for something that are really not supposed to be dense at all. And so then the question comes, well, can we make these things as dense as they possibly could be by increasing the topology? And that was sort of a corollary of the theorem that I gave you before. So if you look at this is sort of the space of the theorems, and even if you move up, I mean, okay, for a non-dense set, this is, again, this is remarkably dense. Okay. And the idea behind sort of proving this corollary then is sort of linked to the existence of surfaces that have so-called long systole. This means they have large injectivity radius everywhere. And because you have this, you can sort of exponentiate for very long times. And if you can exponentiate for very long times, then our theorem tells you that you're pretty close to an actual simple complete geodesic. Okay, so that's sort of the idea behind that. And what's interesting about this theorem is that how do you prove a theorem about correct drawings is by making bad drawings. And that's of course something that when you work in geometric topology you're used to all the time, is that bad drawings we make, I mean bad drawings, we do these, this is what I do on a daily basis. I mean I essentially, you know, my children for a long time they thought I was just a designer of underpants or something. I mean because that's all I sort of did. I kept drawing these surfaces and these pairs of pants and things like that. And this is how you actually prove that. So the idea is that you sort of exponentiate from the surface in both directions until something bad happens. And what is something bad? It means that your geodesic ceases to be embedded, and then you sort of analyze the topological cases. And so this is, for instance, just pictures from an analysis of one of the topological cases. I don't want to get into how this works, but essentially you sort of break things down into cases and you do bad topological drawings. I mean, keep in mind, I keep saying bad topological drawings, but these are what I love to do on a daily basis. And then and you analyze them, and then you realize what's going on, and you construct the geodesic that you want. Okay. Part 3. So we started off with looking at imaging, illustrating sort of a play moduli space. Then we sort of looked at points in a moduli space, so surfaces of hyperbolic surfaces, and looking at drawing on these hyperbolic surfaces. And now we're going to make a moduli space out of drawings. Okay. So we're becoming fully meta. And while I do this, what I need you to do is the following thing. So I'm going to pass these iPads around. I mean, you're going to pass them around. I'm not going to pass them around. But anyways, and the goal is very simple. What you do is with your finger, you draw something, and you have to go from the left to the right. I figure, you know, with a bunch of mathematicians, we have to make the rules really simple. Left to right, okay? And then you do this, and you get some drawing, and then you can add colors if you want. You can play around with the colors, and so on and so forth. Okay, so I'll pass these around. There's 2 of them. And don't worry about the terms and conditions. Just pass them around. There we go. Okay. And I'll tell you sort of about the origin of where this came from. So this is a project that we put together with Bruno Teheux, aided with, by Mario Gutierrez and René Gerards. And the goal came from something that was, so in abstract art, you have there's a lot of geometric shapes that appear, as we know. And these seem to have a certain equilibrium. And what we talk about, when we talk about equilibrium in mathematics, it's a sort of a very different notion from how people talk about equilibrium in art. And we were sort of wondering whether it was possible to question the equilibrium in art from a mathematical point of view. And so there's lots of instances of how people and artists were interested in this equilibrium between abstract shapes. So Paul Klee is of course an example. And the whole school in the Bauhaus school, they were all obsessed with these questions. And Kandinsky was one of the people who really pushed this. And Kandinsky had theories about how these different shapes should behave, how they should relate to one another. And in particular, he was persuaded that different shapes had colors. And he went around and he thought, for instance, that discs or circles were blue. And he was the absolute authority on this. So he would go around and said, don't you think that circles are blue? And everybody would say, yes, of course, circles are blue, Kandinsky. You're right. And so this is the only way people could possibly have told him that circles were blue. I don't see, anyways, but he was absolutely persuaded that sort of shapes had colors and how they related. And so we were interested by this. And so we decided to ask participants. We crowdsourced thousands and thousands of elementary shapes. And we asked people to choose colors for these elementary shapes and to see sort of how they related and sort of come out with this, thinking that we will make the ultimate piece of art. Okay, so first of all, in terms of, so this is the average circle that we obtained. Okay, so it's very exciting. We were very excited by this. And by the way, in terms of colors, what is the color, of course, of a circle? It's not blue, it's yellow. Unless you don't, because every single kid tries to make a sun. Okay, so the answer is yellow. So Kandinsky was wrong. But anyways, so this is sort of a circle, and then this is a triangle. This is the average triangle, and this is sort of the average quadrilateral. Interestingly, the average quadrilateral is convex, which wasn't part of the data. I mean, it would have been possible that the average quadrilateral not be convex, but in this case, the average quadrilateral is convex. And so here's the ultimate piece of art. Anyway, so we were, of course, slightly disappointed. Disappointed. We weren't really expecting much, to be honest. But what we did was we gave these pieces to sound artists, and we gave them thousands and thousands of drawings, and they sort of turned them into
triangles are our favorite shape.
a piece of music.
Dance to the shapes.
We could do the whole piece, but anyway, so that was a lot of fun, and we worked with 3 different sound artists who created different pieces, and then we had this giant concert in front of 900 people, and that was a lot of fun. That's sort of math outreach in an unusual way, but it was a lot of fun. But there's something that beyond these sort of abstract shapes, something that's always intrigued me, especially because I spend a lot of time drawing on surfaces, and this is something I talk a lot about with my brother, who's a visual artist, among other things, and the idea of what an actual curve is, or an actual drawing, or sort of this primitive thing about a drawing is something that really obsesses both mathematicians and artists. And so we wanted to sort of interrogate that, something more complicated than just a triangle. And these are examples of course, people just drawing extraordinary curves. I saw these, I didn't see these exact pieces, but they have an exposition right now at the Grand Palais, for those who want to say about illustration. These are the masterpieces of illustration that come from the Centre Pompidou that's currently closed. Lots of very interesting drawings. And in particular, this is sort of a piece that intrigued me when I was a child. There's a movie that was made by Clouseau in the 1950s, and what he was interested in was not only the drawing itself or the production or a piece that Picasso had made, but the process by which you make this piece, sort of the creative process. And he was able to, this at the time was quite revolutionary, was able to film Picasso doing the actual drawing. And so there's a whole movie about this sort of creative process, and you see Picasso sort of doing something and then redoing something and then doing something again and redoing something, and the whole process is absolutely fascinating. And so I went through this movie, and I found a bit where Picasso is not. So it turns out that Picasso spends a lot of time drawing naked people, but that's okay. I found a piece where he does not. I don't think this is a naked person. And this whole process, and you see this, of course, for us this is maybe less impressive than I think it was in the 1950s. I mean, we should ask people like Francis who were around then, but the whole process, this whole creative process, is something that's really very intriguing. And and so we sort of wanted to, and this is, I took this at the same, I took this piece here. This is by Len Lee, who was a sort of a revolutionary artist who he created this movie here by scratching on the actual film. Like he scratched this on the actual film. And you sort of see here how there's an interesting relationship between how different drawings relate to one another. So if I show you again, you can sort of do this like that. And it's kind of an interesting thing. And you sort of see how a drawing moves from one to another. And this is sort of the thing that we were interested in. And so, right, so Lifeline's demo, I've already done that. So I've given you the iPads, and I hope you continue to do drawings because you'll maybe see some of them at the end. Okay. And so we sort of crowdsourced, again, drawings, and we had people do this with this simple instruction, draw from left to right. And we got lots, and this is from our first harvest. These are different drawings that people did. Notice that the zones have different colors. If you're desperate to ask me a question at the end, you can ask me where the colors come into play. And there we go. And then we did the second experiment started in the beginning of last year, again at this same exhibit. And then we went to the Universal Expo in Osaka, and we crowdsourced thousands and thousands of different drawings. And these are just some of the drawings that we got. I mean, we really have, I think by now we have over 50,000 drawings, but these are just some of them. This one was in Switzerland. This one was in Japan, as one might expect. And so we have lots of these drawings, and we're interested into how they relate. And so there's different things that we did with them. So we decided again to take sort of an average, to try to, this is what the average from the first harvest looks like. And so, I mean, my joke at the time was that this is going to be the world's most expensive experiment to find out that the average drawing is a straight line. Right? But of course, it's not exactly a straight line. And this is sort of what you get when you go to it. And there's this sort of intriguing part in the middle. I mean, first of all, the average is essentially a simple drawing. So to relate to what we were doing before, there's essentially no self-intersections. All the self-intersections that we see now are essentially, I think, due down to errors of approximation. But I think that on average, the drawing that you get is really a simple drawing. And the other thing that we were very interested in is to look at how people actually did their drawing, sort of intrigued by the Picasso movement. And so this is an example of different drawings and looking at how people draw. So this is sort of, forget the drawing itself, just look at the movement of the fingers that people did. And so for this particular experiment, we had them listen to music, and then the three drawings, people were listening to the same piece of music for that one. And then you can sort of see how drawings relate to one another. And so I'm going to, so of course you can do morphings between drawings, and what's interesting here is that we chose the first drawing and the last drawing, and then we looked at the space of all possible drawings, and we let an algorithm choose the drawings that were in between. And I'm going to explain what it is that I mean here. And so for this, we sort of needed a notion of distance between geometric objects. And this distance between drawings that go from the left to right, there's a distance, or a geometric distance, that makes a lot of sense, which is called the Frechet distance, or the dog leash distance. And the way it works is, first of all, I mean, you put one drawing on top of the other, first of all, so let's give them two different colors so we can sort of see what's going on. And you think of it, I mean, traditionally it's you have somebody walking a dog, but there's the dog and the person walking the dog are at equal footing, so I turn them both into ants. Okay, and you sort of go along this, and the whole time you have a leash between them. Okay. Oh yeah, and I did this by hand. I mean, so this is why after a while the ants got old. Okay, so what really matters is the leash. And on this very slow computer, we hope that it will get it. And so you go through one different drawing with one point and the other drawing with the other point. The rule is you're never allowed to go back. So you have to go forward on the drawing. Okay, so you're not allowed to move backwards. And then you do this, and eventually, if the computer allows it, we will get to the end.
Are you parameterizing by constant speed?
So that's the thing, is that you're allowed to change the parameterization.
Even on the speed, so it's not...
Yeah. So I mean, you can, if you want, you can parameterize one of the curves. So I'll get to what this actually means in just a second, once we make it to the end of this. But the point is that you parameterize any way you want. And then you look for when was the leash the longest? So in this particular case, this is roughly when my leash was the longest. And then what you try to do is you try to look at all possible parameterizations, and you take the parameterizations, or a pair of parameterizations, so that the least was the shortest. And this gives you a notion of distance. And this is what Fréchet distance is. So it's the least amount of needed leash length to go along the two curves. Right? This is a natural notion of distance. Oh, and this is sort of the question for the colors, is you can sort of guess what the colors here of zones A and B should be. But the point I want to make is that you have this gives you a notion. This means that any two drawings are related, and you can relate them with a distance in the space of all possible drawings. Right? And the space of all possible drawings is sort of this infinite dimensional set. And let's have a look, for instance, at what you all drew while you were here. Okay, so let's look at the drawings that you actually did. If I can, there we go. So let's see here, let's reload this. So these are all the drawings that you did. This is page 1 out of 2, and there's all these drawings. And you get this, so these are all these wonderful drawings that you did, and what you can do is you can take two of these drawings, for instance, this one and this one, and you look at the neighborhood of all these drawings. And so what this is, first of all, there should be something that appears, whoops, not there, there. There we go, whoops, sorry, here, I'll do this again. And so those are the drawings, and what we've done is we've parameterized the rest of all the drawings with respect to their distance to the two drawings. So we chose those two drawings, and after a while, the other drawings will appear. Or not. Oh, there they are. And so what we're sort of getting a glimpse at is some sort of two-dimensional projection of the space of all the drawings that you did. Okay, so of course this is a very relative point of view depending on where you are in the space. Let me show you one other thing here. So what's sort of interesting is that, so here we have the gallery of all the different drawings that you did. So for instance, if we take this drawing here, and I'm really choosing this very randomly, so please don't, there. And what we can do is we can sort of see how these two drawings relate. And so we press the postcard button, and now you can sort of see how this is a morphine that goes from one drawing to the other drawing. And you can sort of see how these different drawings relate. And you can do this for any one of these drawings. And the film I showed you at the beginning when you sort of did the morphine, what it was is we were looking at that as a metric space, and we were going from one drawing to another drawing, and as we went along in this metric space, or a discrete approximation of this metric space, the drawings that we were seeing as we went along were these closest drawings to the geodesic path between them. Anyways, with this, I'm going to stop.
Is your infinite dimensional space geodesic with this distance?
Yes, it is. Yeah. Anyways, thank you very much.
Questions or comments?